Hello, everybody. I'm Zach. Sorry I was late. I was on the train. So, yeah. So we've had a presentation like this before, Networking 101, more or less. This is version 2. Version 1 was pretty bad. Version 2 is a little bit better. And we've had actually some conversations about what to teach or what to say in this presentation. If you guys feel like it's too much or too little, after the presentation, the end, let's write down what you guys want to learn, what you guys want to know, so we know what to make next time. So this one might be a little too low, a little too basic for some of you, and maybe a little bit too advanced for the others of you. So we'll see. But ask questions, and we're going to have a breakout thing later. I have about 6 routers and 10 wires, and we can actually make a demo network in here. They're in a bag, so there's nothing to look at yet. But we can all kind of break into groups and pretend like we're different buildings and maybe actually make the network that I show in here. I prepared for about 20 minutes, so maybe that won't work. We'll see. So what's covered? This is kind of an intro class. We're going to be talking about, it's beginner to intermediate. We're going to cover IP addresses, subnetting, basic routing ideas, and routing protocols, and then kind of what that looks like for NYC mesh. So some of this you guys may already know, but it might be good to see what the proper way that it is. So when you're doing installations, you can kind of hang on to it, So IP addresses, and for those of you who know that this is IPv4, not IPv6, just 4 for now. They're just the way they sound, they're an address. So it's like a city, street, and a zip code kind of idea, or a city, street, building kind of idea, where you have this number, in this case 32 bits long. It looks like this ones and zeros right here. And that routes you, it tells you where in the world you are. And so you chop the number, in this case, into 4 parts that are from 0 to 255. And so an example is something like 198.51.100.5. And so that tells you an exact computer in the entire world and how to get to it. For example, maybe 198.51 is some company. .100 is maybe one of the floors in their company, and .5 is the 5th computer from the elevator or something. When you send data between 2 computers, it also tells you where it comes from. An example of a network that uses this, you could have 2 laptops that are plugged together, and they will have IP addresses that are adjacent to each other, and they can now talk. So there you go. But there's a little more to the story. You can't just choose an arbitrary number. The number has to come from the organization you're part of, and it has to be kind of, how do we know which part of the network number is for the computer and which part's for telling you how to get to the computer? And so what you do is we make something called a subnet. And we take some of the numbers of the 32 bits and we choose where to divide it. And the first part is called the network part, and the second part is called the host part. And so the network part is telling you which network in the world you're part of, and the host part is telling you, once you're in that network, which computer number are you, right? So in this case, we chose to split the number and at the third number in, so 24 bits for the network and 8 bits for the computer. So this network can have 256 computers on that one network. Another example is you could choose to split the number in the middle, and so 16 bits are for the network and 16 bits are for the computer. So in this case, we would have 198.51 represents which network in the world. There's only one like that. And then you can have 65,000 computers on that network. So the range that's valid is kind of like this. You can fill in the second 2 number with any valid number. Just out of curiosity, is this above people or below people's knowledge? Raise your hand if it's above your knowledge. You just learned something. Okay, good. Okay. Just curious. No shame if you don't know this already. It's just I'm trying to get a survey. Okay, So because we chop these numbers at a certain point, maybe you chop it at 3 numbers in, or 2 numbers in, or 2.5 numbers in. You can chop it anywhere. There's a common way to call these networks that are chopped, and it's called a subnet. And we say something like, this is a /24 or a /16. And that means that you've allocated 24 bits in the beginning to the network part. Or in the /16, you allocate 16 bits to the network part. And so you could talk about that entire network that has 65,000 computers as saying 198.51.00/16. So you just choose the 00 number, the first number in the network, and you say how big of a network it is. And that basically represents the mask. It's like hiding the rest of the network underneath that global number. All right. The 16, the slash, whatever the slash is, that is the mask, and it shows you how long the first part is. And so the second part is the rest of it. Okay? And so we call it a prefix. And a good analogy for the real world is this is like a zip code. Right? If I live in 10001, we all know that that's in Midtown somewhere, and so if you want to deliver a package to 10001, it doesn't matter where within that area I live, you just first send it to that area. And so this is a way to kind of represent all the computers in that network over there, right? And you're just, because it's globally unique, you can chop the network to that part. But in the same way that a zip code has many different houses inside of it, and this /16, for example, could have 65,000 computers in it, you probably don't want to use it as just one network. You want to subdivide that big network into small networks. And so an organization, for example, maybe like a county level, could get maybe a /16 network, a pretty big one, and then they can subdivide it into smaller networks like a /24 or some other size. You can make other sizes 27, 28, 23, 18, whatever you want, as long as it's smaller. And so, for example, you can make 198.51.10.24 and 2.0.24 and so on, all the way up to 2550/24 within this 1/16. So any size within there that doesn't overlap, you can chop it up. And so the reason we might even think about doing this is when we get to the next topic, which is routing, you might, like a zip code, route over to Facebook. They're over that way. And they have some really big allocation, some really big network. But we don't know what's inside of their network. And it doesn't matter, because if you're going to deliver something inside, if you're going to talk to the messenger or the photos, it doesn't matter until you get to Facebook which thing is going to be inside there. Same thing, if you're going to have traffic come to your block, you don't care where on the block it comes. After it gets there, then it goes in to a smaller part. Okay, so here's an example. You could have 2 organizations or 2 counties or 2 somethings, and they have smaller networks inside that are somehow connected. But when you're far away, you don't care what's inside the giant circle. Inside, they subdivide it somehow, and then these organizations somehow connect to each other across an area. But
the subnet is the outer part of the inner.
They're all subnets, but this is a big subnet, and these ones are subdivisions of it inside of it. So in this case, every small circle is a subdivision of the large circle.
It's a subset.
A subsubnet is still a subnet. It's just more divisions. Yep, go ahead, Ron. Sure, I'll talk about that in the next slide.
Oh.
So I mentioned that numbers, well, maybe in 2 slides, but this is the prerequisite slide. The numbers I mentioned are globally unique. Only these numbers tell you where in the world your computer is. However, sometimes, like if you buy internet from Verizon, they only give you one address. And so what you'll do is you'll take that address, and you can't split one address into 2. So you're going to have something called private IP addresses. And these are numbers which you guys can use in your home, and somebody else can also use in their home, and another person can also use in their home, and you can use it over and over again. They're for private use. So you'll never see them in the world, but you might see them in a private network. And so there's some pre-designated address ranges that are just for that. And they're pretty large. There's even a /8. So NYC Mesh uses these addresses. We basically make private networks between our homes. And I go into a much larger diagram in a second. So the way that that works when you buy internet, for example, is you'll have a laptop or something inside your home. You'll have this home router, and you'll have internet. And inside your home are private addresses, and outside your home are public addresses, the one that identifies your computer to the whole world. And as the traffic goes out, the router changes the address to look like it's coming from your public address. It goes to Facebook or whoever. It comes back, and then the router changes it back to a private address inside your home. And we do this on the mesh as well. All of the exit nodes where the traffic goes to the internet from the mesh, they exchange the private address inside the mesh for a public address outside. Yeah, sure.
In that process of changing, is there a one-to-one mapping, or does each private address get one?
I'll ask you, if you want to ask a question after the state, then I'll get it to you.
Yeah.
Okay. Does one private IP address map to one public IP address?
You could do it that way. Most people don't. Otherwise, you would need as many public as you have private.
Yeah, okay.
So there's a thing, part of the NAT will allocate a new connection outgoing from a different port from the inside. So
Got it.
they make a mapping, a temporary mapping.
Cool.
Yeah. I'm going to get to your answer, Ron, by showing that how we build up this into a larger network. And then that basically is NYC Mesh. So if you have that situation where you have this NAT thing at your home to do that translation, when we break it down into the parts, what we get are, there's one router which has an outside plug and an inside plug. The internet provider gives you one public address. Inside you have a private addresses, and the router does NAT. That's it. But how does the router know where to send the data when it goes out? And for this, we have to understand what a router is. A router is just a computer that has multiple network plugs, and it has a table which tells it where to send the data depending on the destination address. And so here's an example table. We say, if it's going to a private address inside the home, go out plug number 1. If it's going to the internet provider, go out plug number 2. And if we don't know where it's going anywhere else, then send it out plug 2 and address it to the internet provider. Right? And so in this way, we cover every possible case. We cover if we want to talk to the inside of the house from outside, if we want to talk to outside just on the network we're sitting on, and if we want to go far away but we don't know where. All right? And so in this case, it's still like a post office. It's either our zip code that we're already in, and so if you send it to the post office, they'll just say, yeah, that's a local mail, and they'll drop it in the bin. Or they'll say, I don't know, it goes to the central office somewhere else. All right? In a slightly larger case, if you had 2 homes, let's say you own 2 buildings next to each other, or something, or you have a friend, and that are next door, and you want to print on each other's printers, and you want to play games with each other, and you want to share files, and you want to play a video on his Chromecast or whatever, you could have 2 homes that have the same setup, and you put a wire between them, a certain kind of wire with a certain kind of router, right? Not just any wire. But in this case, we have 3 networks. We have the we have the home network 1 with the home network 2, and then a wire between them. And you would likewise make a table on each router, and you'd say, if it's going to my home, go out port 1. If it's going to the public internet, go out port 2. And if it's going to the other home, go out the 3rd port. And if it's going to the other home's network, go out that 3rd port and address it to the other home. If it's going out to anywhere in the entire world, send it out my internet connection. And if mine is down, send it out their internet connection. Right? And then the same for the other home. Either it's here on this plug, outside, the other home, and that's it. Right? And so you have to make this kind of table. But you see it's quite a bit longer than the first one. If you had more than 2 then you have to start getting into this kind of situation where you plug lots of homes together with lots of different wires. If you had just 5 homes, you'd already have 16 entries in the table, at least, depending on what you're doing. And adding a new home is going to be kind of painful because you have to plug one more wire in somewhere here, or maybe just a couple of them, and then go to every home and change every home's network to know about the new home. And that's not very fun. And then what if the middle goes offline? You already told every router, go that way to get to the other home. So now you have to go back to all the other ones and change them and say, don't go through the middle one, it's not there, right? So that's not going to be very fun. So that's why so far what we've done is what's called static routing. When you make this table, you just say, to go over there, go through this way, right? No matter what. And if it can't deliver it, then that's it, right? There's no tracking, right? It's just, it doesn't work, it drops, right? So in that case, we introduce something called dynamic routing. And the dynamic part of it means that it's going to change depending on the situations of what's out there. So suppose, for example, there was a way for each of these routers at each home to talk to each other and say, I see this network, what do you see? And the next one says, I also see this, and I also have this one, I also see that neighbor. And then they all exchange what they can see with each other and form this topology so they all know about it. And if one goes off, then they all learn that that one is missing now, right? So that's what we do here. And so, for example, in the same situation, we might have all these little tables that are exchanging with the one that's next to it, and they all learn about each other and decide what to do, and so they form some kind of global table. And it's automatic in that sense. This is what's called dynamic routing. So now we only have to set up each router. We don't have to go back to every home to set up every home to talk to every home. And so if a router goes offline, there's success, and if we add a new one, it just learns about it with no problem. But what other problems can we see with this previous, what didn't we solve by adding dynamic routing? We didn't solve the problem of all these extra wires, right? So if you want to plug in another home, you have to put at least some wires to some other homes, add more addresses, do a lot of work, and it's not really scalable. If you do more than, say, 10 homes, you end up with at least maybe 25 connections per home, and I'm not sure you can even find a box that has that many plugs for what you're trying to do. So it's not really very fun to continue that. And so this is when we kind of formed this new idea about a mesh, which is basically just dynamic routing and not intending to connect every home with every other home. And so you could make, for example, a neighborhood network where some of the homes plug into the neighborhood network, which is maybe in the middle of the block or something, or it's at 2 ends of the block. And you could do something like this. So now you have one box somewhere in the middle of the block, and you run a wire from every home to that one box. And now it's very easy for every home to plug in. They just have to run one wire, not 10 wires. But now there's a middle part, which is a point of failure. And so you could make maybe 2 of them. You could have overlapping boxes. And now instead of plugging 10 wires into 10 homes, you plug in 2 wires to 2 boxes in the middle. And now you have what you used to have, where it goes offline. There's no problem. Some routers can only run 1 wire if they're lazy. And you still have all the dynamic routing capabilities. But that's not what NYC Mesh looks like. We don't have a box in the middle of a block, although we'd love to. We're a bunch of antennas, right? So the difference between the wired version and the wireless version is just that wireless, if you're an expert, this is wrong, but it's close, right? Wireless is just Ethernet over the air, if you want to call it that, right? And so every wireless network is just like the wires. They're just now wireless. We'll skip that for a second. And so you have this kind of situation where you just form that same mesh where some number of routers can see some of the other number of routers. They have a dynamic exchange of all the routes, all the prefixes, the subnets, with each other over the air. And they report what neighbor they see, what other neighbor they see, and they do that over and over again. in the wireless world, although it is like Ethernet over the air, there's a couple different modes. One mode is what you guys are probably all used to, if you're, we're all used to, is infrastructure mode. This is when you have a wireless box in the corner, what we call an access point. And even if you have two laptops or your laptop and your cell phone and they're wireless, all the traffic goes to the router, it goes to that access point, and back to the other device. One of the main benefits of this is that device mediates the traffic. And so it says, it's your turn to talk, okay, now stop. Now it's your turn to talk, okay, stop. And so you can be very efficient with the air, with the signal in the air. But it leads only one point of failure. An alternate, which is more meshy, is this ad hoc mode. And in the ad hoc mode, there's no controller, just everyone talks whenever they want to. So it's more akin to the wire situation where a wire will just, maybe you'll have a collision, maybe you won't. And so obviously the benefit is that there's no one in charge of that wireless network, but the downside is that it's less efficient, there's collisions, and if there's something very far away, it could interrupt whatever is right next to you. So depending on the situation, we may use one of these or the other of these. So wireless networks like NYC Mesh, as we just talked about, they're dynamically routed wireless networks where you share routes, you share those subnets between your neighbors. And each of you who has a node has a subnet, and you announce it through the routing protocol to your neighbors. And so they can see in a list, they have a table. Right now our table's about 85 subnets long, which means that's just how many we see, although there's subdivisions within there. And so you can see all of your neighbors in that way. It's like an extended version of the multiple home situation. And you can also use wired and wireless between homes depending on what is out there. So the dynamic routing protocols, I just talked about a generic one, but there's a bunch of them out there. There's 50 protocols or more. How do you choose which one you want and which one's the right one? And they all operate a little bit differently. Some of the lies about wireless is just Ethernet on the air, not true. But depending on what you're doing, you may choose a different protocol. Here's some examples. In the situation that we're in the example later, it's going to be the protocol called OSPF, which is a very simple protocol. We don't use this one very much on the mesh, but there's a couple other ones. These other ones, like OLSR, is used by Freifunk in Germany, and it's good and bad. And Batman was made by them, and it's good and bad. And they all have various positives and negatives, depending on what you're doing. Some of the downsides of them are, for example, a couple of these protocols only scale to about 30 nodes on the network, 30 routers. And some of the reason why is that in this example right here, this is actually a state table distribution type thing where every time you add one node, you have to tell every other node that it's been added. And so you have to send 30 updates in every direction on every link, and you say, hey, I found a new one, I found a new one, I found a new one. And that ends up causing a lot of traffic and a lot of churn in the computer. And so it takes a lot of time, and so maybe scaling past 30 nodes or so starts to be a pain with some of these protocols. But that can't be the case because the internet is a mesh and they have a dynamic routing and it has hundreds of thousands of networks. So somehow there has to be some routing protocol out there that can handle changes all the time without causing lots of pain and scaling past 30 computers. The internet uses one called BGP. We also use this. It's not the only one we use, but in some parts of our network we use it. And an example of the reason why it scales is that it doesn't care about the link itself. So if the wireless goes up in performance or down in performance, it doesn't change the direction of the traffic. It's not changing the direction of traffic also for any minor reason. If, say, in that zip code way over there, someone moves one house over, it doesn't send an update. It doesn't matter. And so in that sense, it doesn't care about things that are far away. Whereas in the other protocols, every change, every time is going to tell everyone about every change. and so it takes a lot of traffic. So what we do in the mesh is we take a hybrid concept of that internet style and the local style, the local continuous updating style, and we blend them together. And so we make a hybrid topology with many stable nodes. These are the nodes that we, for example, rent space on rooftops, or they're hub nodes, and we pay a little bit of extra money to put good antennas on them. They're stable, and they're kind of like the county post office. It's not going away. It's not going away for the next 50 years. In our case, maybe 1 or 2 years, right? But that thing's going to be there, and your grandchildren are going to know that post office is there, right? And then we have a series of semi-stable nodes where we are pretty sure it's going to be there for a while, and it has some good antennas. They're not super great, but it's going to be there for maybe a year or two. And so this is kind of like your neighborhood post office. If they take the building down, then the post office is gone, but they're probably not going to take it down anytime soon, right? And then we have in the next level of computers, or the next level of the mesh, is just rooftops on buildings. And people move, people come into buildings, they leave, somebody falls on the antenna, all kinds of things happen. We had a couple of fun things this last week where someone just moved and I don't know, nothing, they just were gone. And somebody else in the building couldn't use the mesh. We had another time where somebody like fell on the antenna and it broke, and like these things happen, right? So that's kind of like the delivery routes, if we're talking about a delivery type of example, right? So maybe the delivery truck will drive this way this month, but maybe the road's closed, it'll drive that way next time, and so that kind of changes here and there. And so we use these big table BGP type connections that exchange large amounts of the routes between them at the highly stable sides. And it doesn't care about what happened in that neighborhood. It just cares that that neighborhood is that way. It's over there. So if we're sending traffic to Brooklyn from Manhattan, it's always going to Brooklyn, one way or the other. And that helps make it so we can scale past a small number of computers. Example here is a hybrid thing, right? We use BGP at the supernodes, and we use more agile protocols in the neighborhoods. And so, you may have post offices like this. We consider them as mesh neighborhoods, like this. This is our thing as of today. I think 254 nodes, something like that. The blue dots are what we call hub nodes or super nodes. They're the stable nodes that are going to be there for some years. The red dots they're not worse. They're just not super nodes or not hub nodes. They're ones that are people's homes, they're buildings, they're all kinds of things. And they connect with each other as well as connecting, or they can connect with each other, and they do connect to hub nodes or super nodes. And the super nodes and hub nodes connect to each other as well. For example, the link that Brian showed earlier, where we have these super fast antennas, we have these highly stable connections that we expect to be there for some years, whereas some of the red dots may come or go. Actually, I didn't know I was going to go last, so there's no break. But if you have any questions, go ahead and ask them at this point. Shay.
Do you have any ranking systems for assessing like stability or like access to hub nodes that help you prioritize or weight different potential nodes?
We don't have a strong formula. It's mostly if it's a tall building and they want us there, we're not like sneaking on the rooftop. We would never do that, right? But they want us to be there. Maybe like the owner said, yeah, sure, I'll pay for all those antennas. You're like, cool. They're invested in the idea, and we can go back there many times and do it again. And in that case, they're quite happy that we're there. Most of these blue dots are that way. Most of them are that way. Or if it's a building we pay for, the dark blue dots are the ones that we pay for. Or like here, we don't pay for it, but the school's not going anywhere, for example. So,
Here you go.
Here, let's just keep this mic up here, so we don't have to make Jolly run back.
You just put the hand up and we know where it's from.
Yep.
Can you just go over one more time the advantage of the non-internet networking protocol? Like you referred to it as more agile, but all I remember is the all I remember is like the factorial of alerting every other node.
Yeah, so the good thing about it is that it's kind of especially good at self-healing, especially good at self-discovering what's next to you. All of these protocols, they all do that, and most of those other 50 that I didn't list also do that. And so the nice thing is they also, for example, actually I took this line off this version, but many of these will find out what the link quality is, look at the Wi-Fi signal, and they'll say, oh, this signal's pretty low, and oh, I can hear that one pretty good, and then they'll preference that. So rather than using, like in the very beginning here, we had these tables and there's a priority. So for example, you first want to go out the internet that you have, and this is like this is the static route with 2 houses, right? And then if your internet's not available, then you want to use your neighbor. And likewise, the neighbor will first use their internet, and then they can use the next one. But in some of these protocols, they'll self-adjust the priorities, and so you can get, a node that's a little bit farther away will be a lower preference. But if nothing's close, it'll use that instead. And so the bigger ones, the BGP type ones, they don't really do that. You can, but it's more complicated.
Thanks.
Sure. Yeah, here. Yes, sorry.
The light beam antennas that Brian showed were directional. Like, are all the connections pairs of antennas, or are the supernodes, are they somehow omnidirectional with a bunch of things pointing at them?
So we can use a variety of connections in between things. So for example, in the multi-home example, that was all wired, right? And in the same thing but wireless, it's just wireless. You could have 2 things wired and 2 things wireless. So you could have any combo of technologies. In this case, those directional ones are pointing to hub nodes because they're really good at traversing over the urban environment of Manhattan, where we have tons of microwaves and all kinds of signals happening all the time. And so those are directional. They're not a mesh in that sense, but the network's a mesh, right? So going back to these wireless modes, we have, those are ones that are infrastructure mode. And so the benefit of that is that the access point on the hub says, okay, your turn to talk, okay, now you. And so it's efficient and everyone knows how to talk and when to talk, and you get your sliver of bandwidth, right? We have ad hoc antennas as well, but it doesn't scale very far because you'll have somebody that's a block away, they'll be talking very loudly and you won't be able to hear the building 2 buildings away. And so the mediation really helps with that, especially in this kind of environment. So you're right, those are directional, and they're more like a wire in that sense.
Right, so can I ask what kind of antennas the supernodes have?
The supernodes are just the receiving side of that. But we also have point-to-points like the one that Brian showed. We have these more expensive donated ones. However, you can best connect between hub nodes. I could tell you exactly which ones on every node, but not every node, many of them, but basically our goal is to connect them in the best way possible so that it becomes a decent quality community network. Yeah. We see it as like a replacement for wires. Yeah, right behind you there.
Thanks. So just sort of to continue that question, basically each one of those nodes then just goes directly to a supernode. There's no like talking in between.
So we have a couple, you can talk in between. You can use ad hoc and infrastructure on any one node. As long as you can connect somehow between different nodes, you're good. So for example, we have an antenna called an omni-tick, which is it's like a stick that has an antenna that's 360, and it can talk between neighbors. We also have a little sector antenna that's kind of very small, that can talk between neighbors. And we're always looking for more antennas that can talk between neighbors. But when you have some that talk between neighbors, down the line, you might want one that talks to a hub node. So you can get into the neighborhood and then jump around if possible. We don't have as many of those as we'd like, but there's a lot of reasons why
Okay,
it doesn't
so-
scale very far.
And then those neighbor ones are all ad hoc ones.
One model is, the other model isn't. Yeah, there's a couple more modes. There's something called WDS, which is like ad hoc mode, and there's some other ones past that.
Can I just ask, like, I guess ultimately, what's really the benefit of having those at all if really they just kind of don't seem to work that well?
They don't seem to work that well because they don't scale very far and they're not very fast. So people become frustrated with them if they want to use the network for something like internet. But I mean, that's one valid use of the mesh network. It's not the only use. But if you got 2 megabits and if she was using internet, your 2 megabits might be half a megabit, and then like if she happens to be routing that way, yours is 2, but not if Rory is using it. And it's like, okay. So it's hard to say whether they're not exclusively bad. It's just hard to find a good model of it. But the concept is good. And what we do is we even have some points which are not hub nodes. For example, right here we have, you can't see it, these 2 red dots are connected using something that's not ad hoc mode. It's not an omnidirectional antenna, but neither is a hub node. We just point antennas at each other, and they just have a point-to-point. So you can even use little $30, $40 antennas and point them at a node over there. Basically, if you talk to that neighbor and say, would you mind putting this antenna? And he goes, yeah, sure. And when you put your antenna, you can see each other and talk that way.
You can talk to each other. You can talk to each other, but you could also talk to the internet at large.
Well, you would have a node that has many plugs on it. Thank you, Jolly. You would plug many antennas into one node. You'd have like a box that had 4 or 5 ports, and you'd plug in one antenna to a hub, one antenna to another hub, one to the apartment downstairs, one to another apartment downstairs, one to the neighbor on 7th Street, one to the neighbor on 3rd Street, and maybe also one omnidirectional just in case. All right, and you could do that. It happens. And I mean, the benefit of that compared to just putting one antenna is that you now have dedicated performance between all the others. And maybe it's a little bit much for just you to use it, but if you're going to have other people behind you coming through you, you might want to try and ensure that they're going to have a good experience. Yeah. Okay, so that wasn't a very long presentation, but again, do tell us, or tell me, or anyone else, if you have some ideas of what you want to hear in the future. What I do also have for us is we can do this network. And the idea here is if you had maybe 2 blocks adjacent to each other and you had 5 buildings on this block, how could you set up a mesh network between these? And so I was going to demonstrate this for us using wires. And so we can get the sense of what it looks like to wire it all together on these tables here. And we can even plug this into the NYC mesh because this building is a node. So that's possible maybe. And we could, at some point, look at the different tables on each of these routers and see, if I'm on C, we could break into different groups. If your group is C, and you guys all live there, and you want to talk to the people at A, you could look at the table and see that it dynamically routed to A. And then we could unplug one of them and see if it changes. Of course, I didn't make any connection between, so it's only one thing we can unplug and the whole thing breaks, but we can always put more wires. That's okay. This is what I did in 20 minutes time. So do we want to do this? What do you guys think? Would it be of any benefit? Or we can do this during the breakout time. Some people, there's pizza as well from Mr. Donuts, and we can do that and do this at the same time. And everything else. All right? Yeah, I think so, Jolly. Anyone else want to say anything? All right. You? Okay. Thank you, everybody.